Justin, and I'm joined once again by my fellow scientists. I got you can introduce yourself. Tell me your name.
I'm Lily.
Yeah.
I'm Katie.
Now, Lily and Katie. So from the NuMinds vault, what we do is we dig back for lessons that we've had over the past 8 years and find some of our all-time favorites. So things that we're doing here today, you'll have a chance to actually pull it out from the comments below. We'll post a PDF on it. And so we're going to kick off with kind of, we're outside having some fun, and you can see we're keeping social distance, right? So hopefully you have some fun and have a chance to do this as well at your house. So, okay, so our first lesson is about force equals mass times acceleration. And kind of a fun way to test this out is with Lily and some math. So are you ready? Okay, come on over, let's grab your stuff.
I don't know what they're doing.
So as we know, force equals mass times acceleration. And so let's just say, how much does that balloon weigh? Just take a guess.
2 ounces.
2 ounces. So our mass, we're going to say, is maybe 2 ounces. Put that here, okay? Now, times the acceleration. And make it easy, I know it's not the same thing, but let's just say it's about speed, okay? So, how much speed are you going to hit Katie with?
What? Hit me.
Sorry. Oh yes, hello, sorry. You're part of the experiment too. Okay, so come over here, Stand in the grass. Okay, I'm sorry, yes, okay. Thank you for joining us for science. So how much do you want to throw it at her? Just make up how fast.
1 mile per hour.
1 mile per hour. So I'm going to plug this in with 1 mile per hour. Now what is 2 times 1?
2.
Okay, it's pretty easy, man. So in this case, this is for pretend, for an example. This is an easy way to do this. You'll say your force is going to be 2, okay? So show us real fast how much force it takes to pop a balloon. Do you mind just kind of squeezing it and see what it does? Oh, okay. So that was the that was the force to get the balloon to open. So now here's your balloon with the mass. You think about 2. Is that the same? All right, go with your slow 1 mile an hour throw it to. Oh. Okay, so it didn't pop on her, right? So grab another balloon. So tell me real fast, what can I do to increase the force?
I throw it harder.
Okay, so what would you be changing? Would you be changing how much the balloon weighs?
No.
What would you be changing?
Force.
So the force changes because why?
It's going faster. Acceleration.
More acceleration, it goes a little bit faster, right? So how fast do you want to throw it this time?
3 miles per hour.
3? How about 10?
Okay.
All right, so let's just pretend we're doing some easy math here just for fun, for a good example. What's 10 times 2?
20.
So now the last time you had a force of 2 and it was kind of like hit the ground. Now you're going to hit with a force of 2 times 10, 20. All right, 10 times as much. Let's see if it makes a difference. Are you ready? Okay. Here. Try one more time. And you know what? Maybe 10 wasn't enough. Maybe we need to up it to how high?
11.
11. All the way to 11.
Yeah.
So what's 11 times 2?
22.
So now we're going with a force of 22. Oh! Thank you, Katie. Thank you, Katie. Oh, there's stomach. So real fast, we do have some more to show you. This is an easy one, again, kind of easy math you can have some fun with. And so obviously you can go a little bit more deep with this part and actually talk about, like, if you were to measure this with kilograms, and if you could actually take like a meter stick and measure your acceleration using meters, you can actually find the force in newtons. So that's the next level. But yeah, let's take it to the next level. Come with me here. All right, so this one, we're talking about as you start to go faster and faster, what happens. And so
It has water on it.
yeah, I know, so be careful. Be careful.
Guys, don't tell him
What's she telling you?
Don't tell him we're going to dump water on his head at the end.
Okay, so sound and light makes a wave, and this is just a graphical representation, so it doesn't actually look exactly like this, but here's what we're going to do. Sound has this speed, and so it has this speed, and what we're going to do is we're going to actually see if we can get a frequency out of this recorder. So we brought Lily's recorder, and they probably didn't know that you're actually a black belt in recorder player, right? Now, this is actually why your dad was not allowed to play recorder. Watch this. I used to do this all the time. And the teacher would be like, Justin! So we're actually going to use this part because she's going to blow on it and make one note. So play real fast this one note. Okay, so that's an E. That's pretty steady. We measured it out before the video. It's around like 640 hertz. So that's a high E, okay? So she's gonna play a note while riding her bicycle. So if you're able to go outside, great. You can also do this in a hallway as well. Are you guys ready to do this? All right, grab your bike and I'll talk about it.
There's a bike right there.
Okay, so what we're doing real fast, we're talking about the Doppler effect. Here, Katie, come on over, because you want to talk about this too, didn't you? Okay, so we have...
Not the Doppler effect.
You and
Sonic boom.
Oh, okay. So the Doppler effect, what this is saying is for Lily, the sound, that high E, will stay exactly the same. But because we are moving relative to her, right? So she's hearing one note, and she looks over at us, and we're actually like the ones that are observing her. We're going to, as she gets closer, it's going to almost smash that down. I gotta be careful if I say this. It's going to change the frequency. Frequency is going to go up. All right, so let me ask you a question. What happens with the note, Katie, when it goes up in frequency?
Wait!
Almost ready.
Wait!
What happens with the note when it goes up in frequency?
Well, first of all, if she beats the sound,
Okay.
if she goes so fast,
Hey, I know what you're talking about.
if she would go so fast that she would beat the sound, she would make a sonic boom. All of a sudden, there would be a big boom.
So Katie's super excited to tell you about the sonic boom, so I'll make sure I tell you that part. So real fast, what happens when the frequency goes up on a note? So she's coming at us, the frequency goes up. Let's make an observation and see what happens. And when she goes away, it's actually going to extend that note out, and the frequency is going to go down.
But to her, it's actually going to sound like she's blowing the same note.
Playing the same notes. This is called the Doppler effect in action. So, okay, let's go over, and we gotta be super still with the camera. Okay, we're ready.
What do you need to stand
So come all the way over here. So she will hear the same note being played, and we'll ask her, but the note will change for us. Let's listen.
Go.
Did you guys hear it change? Do it one more time, Lily. Now you're probably familiar with this when you hear things like sirens go by or police cars go by. You hear the note getting higher and higher. The note itself is not changing. If you were inside that police car, it would have the same exact sound the whole time.
Thank you, everybody, for joining.
Because it's coming closer and closer, it's smashing that wave, and so the frequency is going higher. Again, medium level science, you can obviously dive in a lot deeper than this. So Lily, this time hold the note as long as you can, okay? And Katie is excited to talk about the sonic boom, so I'll give her a chance to do that too. Okay, we're ready! So once again, she'll hear the same note for herself, but for us, we'll hear a different note. Yeah, there it goes. So you hear the pitch go up and then the pitch come back down. Okay, so when she comes back, we'll ask her what the sound was, but that's something cool you could do at home. You heard me mention earlier that if you can't go outside, you can actually do it down a hallway. Just please be safe, right? You can actually run down the hallway playing one note, and that's the effect. Okay.
Oh, can you stand still for a
You
minute?
wanted the sonic boom part, right? Okay. So the other part is too, like this same effect happens actually with planets. Solar systems and galaxies. So the way that we spin, nothing moves faster than the speed of light, so we can't accelerate the speed of light. But what happens is this: galaxies are spinning and swirling, probably the easy way to describe it. And some are actually spinning towards us because it's so far away, it's spinning so fast, it is changing the frequency of light. And so if you can look online, you can even Google this, the Hubble telescope is able to see different galaxies. Now the ones that are coming closer to us, that higher frequency of light, they start to turn blue. It's called blue shift. And the ones that are spinning away from us, that light, which again remains a constant speed, has a higher frequency and has a red shift. So they can actually look up and see which galaxies are moving towards us and which ones are moving away. So Doppler effect, all the way up to the very, very complicated. You can look up the part about the red and blue shift and the frequency of light and electromagnetic spectrum. So, man, hey, how did the note sound to you? Welcome back. Thanks for doing that.
It sounded the same the entire time.
It never changed once?
No.
Okay. But then for us, did you hear like what we showed a little bit of video? You heard like for us, it went and changed. Cool. Okay. Well, guys, we hope you enjoyed this time from the NuMinds Vault. My name is Justin. We've lost Katie somewhere. Katie, we're signing off.
Wait, we have one more surprise.
What's your last surprise? I never know what to expect.